Hello and welcome back. In this video, I want to begin talking about circular motion, and in particular, I want to talk about a very specific type of circular motion called uniform circular motion. Uniform circular motion is the motion of an object that travels along a circular path at a constant speed. Now, even though the speed of the object is always the same, the acceleration is not equal to zero. The reason is that as the object travels along a circular path, the direction of the object's velocity is always changing. Now, I'd also like to introduce another definition. The period of the object's motion is the amount of time it takes for the object to travel along a circular path one complete time. Now, obviously, the period of the object's motion is related to the speed that the object is traveling at. If an object is traveling faster, it can travel through its circular path in a shorter amount of time. So, the faster the object is moving, the shorter the period. We can relate these two things pretty easily. The speed that the object is traveling at is equal to the distance that the object travels through divided by the amount of time it takes for the object to travel this distance. For an object that's traveling on a uniform circular path, the distance the object travels when it travels along a circular path is equal to the circumference of that circle. So that's 2 pi times r. And the amount of time it takes for an object to travel one complete time around a circular path is what we call the period, and we denote this with a capital T. So the speed that the object is traveling at is equal to 2 pi r divided by the period. And we usually just write this as v. So this is the magnitude of the instantaneous velocity of an object when it's traveling in a uniform circular path. Now, as I mentioned in the previous slide, even though an object is traveling with uniform circular motion and its speed is always constant, the acceleration is not equal to zero. And the reason is because the direction of the velocity vector is always changing. The acceleration that is responsible for uniform circular motion is called the centripetal acceleration. And I want to walk through a derivation of how we come up with a formula for the centripetal acceleration. So I'm going to draw over here on the right the path of an object that's traveling along a circular path. And I want to consider, let's say, an object that starts here. So when we talk about uniform circular motion, we usually describe the position of the object with a vector that points from the center of the circle to the point where the object is. So I call this the position vector. So if the object starts here, this is the initial position vector. Also, remember that the velocity vector is always perpendicular to the path that the object is traveling on. So if the object is traveling in a circular path, the velocity vector is always tangent to that circle. Now, one thing I want to point out right away is that you should notice that the velocity vector and the position vector are at 90 degrees from each other. Okay? Now, this is a very, very important idea, because it's sometime later, so let's consider sometime later the object is going to move, let's say, up here. So now I've got a new position vector that describes the position of the object. I'll call that r final for my final position vector. And now the object has a new velocity vector as well, because it's now traveling something like this. So I could describe the change in the object's position using this angle right here. So this is the sort of angle that the object has traveled through in its circular path. Okay? Now, as I mentioned before, the velocity vector is always 90 degrees with respect to the position vector. So if my position vector rotates through an angle delta theta, my velocity vectors will also rotate through that same angle. So, for example, if I take my velocity vector, my initial velocity vector, and I move it up here, this angle between my initial and final velocities is equal to delta theta. If you're having a hard time seeing exactly why this is, consider something like a piece of paper, right? So the adjacent sides on a piece of paper are at 90 degrees. Of course, if you take a piece of paper and you rotate it through some angle, all four sides of the piece of paper rotate through the same angle. This is the same kind of idea here. I have my position vector and my velocity vector, and they're locked in at 90 degrees with respect to each other. So when my position vector rotates through an angle delta theta, my velocity vector has to rotate by that same angle delta theta. Now, this is a really important concept because we're going to use this to calculate the acceleration. So remember that acceleration is equal to the change in the object's velocity divided by delta t. So what I need to do is come up with some way to describe the change in the object's velocity. So looking over here, we can see already kind of what this looks like. So let me draw a picture of my initial velocity here. My final velocity looks something like this. So I've literally just drawn this picture over here, over on the right. Actually, my final velocity vector should be the same length as my initial velocity, so something like that. And what I want to do is I want to find the change in the velocity. So that's the length of this vector right here. This is delta v. And the first thing I want to point out about this is that the length of this vector is approximately equal to the arc length that's traced out by my velocity vector when it rotates through this angle, delta theta. So what this means is that delta v is approximately equal to the length of this vector times the angle that this vector is rotated through, right? So the change in the velocity is approximately equal to this arc length, right? And remember the arc length formula is the length of this vector times the angle that it rotates through. So I can plug this into my formula for acceleration, and I see that my acceleration is v delta theta over delta t, or just v delta theta over delta t, like this. Now, at this point, I'm still not quite done, because most of the time you're not going to be given the rate that the angle is changing. So if I knew the rate that the angle was changing, I could plug it into this formula and find my acceleration, but most of the time that's not going to be given to you. But I hope that it's obvious that the rate that the object, that this angle is changing, is related to the speed that the object is traveling at. So what I'd like to do now is come up with a way to describe delta theta over delta t in terms of the speed that the object is moving. And the way I'm going to do that is by calculating a formula for the speed that the object is traveling at. So remember, velocity is change in the object's position divided by change in time. So I need a way to describe how the position of the object changes when the object rotates through an angle delta theta. Well, again, we'll do the same kind of a trick. Here's my initial my initial position. Here's my final position. The change in the object's position is this vector right here. And again, this vector that describes the change in the object's position is approximately equal to this arc length that's traced out by the position vector when the position vector rotates through this angle, delta theta. So the change in the object's position is approximately equal to the radius of this circular path times delta theta. In fact, we can see this actually is the distance that the object travels when it goes from here to here, right? The distance the object travels is equal to the length of that arc, which is just r delta theta. So if I plug this into the formula for v, I see that v is equal to r delta theta over delta t, or if I factor out the r, it's r times delta theta over delta t. So what this means is that delta theta over delta t is equal to v divided by r. So if I plug this formula into my formula for acceleration, I get that this is v times, and then we say delta theta over delta t is equal to v divided by r. So my centripetal acceleration is v squared divided by r. Now, this gives me the magnitude of my acceleration, but what about the direction? So let me use green for the direction of the acceleration. Now, remember, acceleration is change in velocity over delta t. So obviously my centripetal acceleration is going to point in the direction of delta v, and that's something that looks like this. Now, if I'm starting here and I end here, what I've calculated here is more precisely my acceleration halfway in between. So if I take this acceleration vector, this delta v vector, and I move it halfway between these 2 points, this is kind of what my acceleration vector looks like at that point. And looking at this picture, we can see that my acceleration vector is almost exactly pointing back towards the center of this circular path. In fact, had I drawn everything just perfectly, my acceleration vector would point directly back towards the center of the circular path. So centripetal acceleration always points towards the center of the circular path, and its magnitude is given by v squared divided by r. So let's go ahead and consider a couple examples. The first example says a centrifuge is used to create an acceleration of 6,250 Gs. The radius of the centrifuge is 5 centimeters long. How fast does the centrifuge have to spin in terms of revolutions per minute? Okay, so the first thing we need to do is figure out how the revolutions per minute are related to the velocity. The reason is because the centripetal acceleration is equal to v squared over r. Now I was given the acceleration. I was told that that's 6,250 Gs, or 61,250 meters per second squared. So I know what my acceleration is. I also was given the radius of the circular path, so I know what r is. So I need to come up with a way to describe velocity in terms of RPMs, because that's what I'm being asked to solve for. So if we think about this, an object is traveling in a circular path. If the object travels once around its circular path, the distance that the object travels in is equal to 2 pi times r. And the amount of time it takes for the object to travel around this circle, if the object is moving at 1 RPMs, so it's moving 1 revolution per minute, then the time it takes for the object to travel around the circle is 1 minute. So this is for 1 RPMs. What if the object was moving at 2 RPMs? Well, if it's traveling at 2 RPMs, the distance the object travels in 1 minute is twice around the circle. So that distance is 2 times 2 pi r divided by 1 minute. So in general, if an object is traveling at some number of RPMs, the velocity is equal to the RPMs that the object is traveling at times 2 pi r divided by 1 minute, or divided by 60 seconds. So this is how I relate the velocity that the object is moving at with its revolutions per minute. It's the number of revolutions per minute times 2 pi r divided by 60 seconds. So now I want to solve for my revolutions per minute using the centripetal acceleration formula. So the centripetal acceleration is v squared divided by r. And we can write this using this formula right here. This is my RPMs times 2 pi r over 60 seconds. And it's this whole thing squared. Right? It's my velocity squared times 1 over r. Now looking at this, we can see that this 1 over r will cancel with one of these r's here. So I can write this as the RPMs times 2 pi over 60 seconds squared times r. So now if I'm trying to solve for my RPMs, the first thing I want to do is divide r over to this side. So I have a over r is equal to 2 pi times my RPMs over 60 seconds, and I still got this whole thing squared. So all I've done from here to here is I've just divided off this r to move it over to here. Now if I square root both sides and then I multiply this over here, the 60, and divide by 2 pi, I see that my RPMs are equal to, so the first thing I do is I square root this. So I have this as A divided by R square rooted. And then I'm going to multiply the 60 seconds over here and divide by 2 pi. So at this point, I know all of these numbers. I know what my acceleration was, I know what the radius is. So if I plug all this into a calculator, I see that this is equal to 10,600 RPMs. Okay. Now I want to go ahead and look at another example. And this example is a pretty challenging example. So the example here says, a carnival swing ride consists of chairs swung in uniform circular motion at the end of a 12-meter long chain. The chain is attached to a vertical post, and when the swings are swinging, the chain forms a 60-degree angle. Actually, I think it's supposed to be a 65-degree angle. That's what my numbers here on this piece of paper say. 65-degree angle with respect to the post. And the mass of the chair is 220 kilograms. So this question is broken into two parts. The first part asks us to find the tension that's in the chain, and it turns out that's not too bad. The second part then asks us to figure out how fast this chair is moving at so that the chain forms the 65-degree angle. So let me kind of draw a picture of what's going on here. So we've got this vertical post here, and attached to the top of the vertical post is a chain. And then at the end of the chain is a chair. And this chair is swinging around this post in uniform circular motion. And the angle that the chain forms with respect to this vertical post, this angle right here, is 65 degrees. So the first question just asks us to figure out what is the tension in this chain. So let me go ahead and draw a free body diagram for this box. So we've got this chain attached to the box, and then we've got this box here. And there are really just two forces that are acting on this box, the swing chair. There's the force due to gravity that points down, and then there's the tension in the chain. Let me erase the chain. The tension in the chain points up like this. So if this chair is swinging around in a horizontal circle with uniform circular motion, then this chair is not moving up or down. So we can see that the y component of my tension has to cancel the gravitational force. And using this, we can figure out what the tension is in the chain. So what we have is that the y component of my tension has to be equal to the force due to gravity. So the y component of my tension, let's think about this. If this angle up here is 65 degrees, that means that this angle right here in this triangle is 65 degrees. So this angle is 65 degrees. The y component of my tension is adjacent to this angle. So the y component of my tension is equal to the magnitude of the tension in the chain times cosine of 65 degrees. And this needs to cancel the force due to gravity, which is mg. So rearranging to solve for the tension, I see the tension is equal to mg divided by cosine of 65 degrees. Plugging these numbers into a calculator, I can see that the tension in the chain is equal to, 25.2 times 10 to the third newtons. So that's the tension in the chain. The next part of the problem asks us to, oh, that's wrong, I'm sorry. The tension in the chain is 5,110 newtons. I thought that number seemed a little big. Okay, So the next part asks us to figure out how fast this object has to be moving at to be traveling in this horizontal circle with this angle being 65 degrees. So the idea here is that if this object is traveling in a uniform circle, then there has to be some force that is causing a centripetal acceleration. There has to be some force that's pointing inwards towards the center of the circle so that the object will travel in a uniform circular path. Looking at this free body diagram over here, we can see that the x component of my tension in fact points inwards towards the center of the circle. So it's the x component of my tension that is causing the centripetal acceleration. Sometimes when we have sometimes we describe this force that is causing the centripetal acceleration as the centripetal force. Now, it's very, very important to understand there really isn't some additional force that's called centripetal force. When we talk about centripetal force, what we're saying is we're saying the force or the sum of the forces that is creating the centripetal acceleration, and we're calling that the centripetal force. Okay? But it's not some additional force, right? Looking at this example here, the x component of my tension is what's causing the centripetal acceleration. So we'll sometimes call the x component of my tension the centripetal force, but it's not some additional unique force. Okay? Now, I know that the acceleration that this tension causes is equal to v squared over r. So right away I know that Tx is equal to mv squared over r from Newton's second law. So using this, I'll be able to solve for the velocity. Now, I don't think I have enough room right here, so I need to get another script. Actually, I'll just erase this stuff up here. That way I don't have to redraw all this stuff on the right. So what we have is we have that the tension in the x direction, the x component of my tension, has to be causing the centripetal acceleration. So the x component of my tension is equal to mv squared divided by r. So solving for v, I see that v is equal to the x component of my tension times r divided by m, and then I have to square root this whole thing. Now the reason this problem is pretty challenging is, first off, not only is the force that causes the centripetal acceleration not any force in particular, it's a component of a force, but this problem's a little bit tricky because of what r is. If we think about this circular path that the object is traveling in, r is this distance right here. It's the horizontal distance from the center of this post over to where this object is. Now, I've told you that the length of this chain is 12 meters, but r is not 12 meters, right? r is this length right here, the length of this chain. And all we need is the horizontal component of that. So looking at this triangle that we have here, I know that the hypotenuse is 12 meters. I'm trying to figure out the length of this side here that's opposite the angle 65 degrees. So we can see that r is equal to the length of the chain times sine of 65 degrees. Also, the x component of my tension, looking at this triangle right here, we can see the x component of the tension is opposite this angle, 65 degrees. So the x component of my tension is equal to the tension that's in the chain, also times sine of 65 degrees. So if I plug both of these things into this formula here, I see that the velocity is equal to the tension times the length of the chain times sine squared of 65 degrees. Right? I get one sine from the tension, and I get one sine from this r. And this whole thing's divided by the mass, and I still have to take the square root. Now at this point, I just have to plug all this into a calculator. I found the tension in the chain. That was from part 1. I know that's 5,110 newtons. I can calculate the sine of 65 degrees with a calculator. The length of the chain was given to me. That was 12 meters. And the mass, that was given to me as well. That's 220 kilograms. So if I now just plug all these numbers into a calculator, I see that this is equal to 15.1 meters per second. So that's how fast this object has to be moving to have this chain be at an angle of 65 degrees. Now, at this point, I think I'd like to end this lecture, and in the next video, I want to talk about some additional examples where we use centripetal acceleration, such as the motion of an object that's orbiting a planet.